Everyone, we are back and we are at Pset 3 solution videos. So let's go ahead and let's get started. So look at the image below, identify the following defects, state the dimensionality defects. Some defects may or may not exist. So let's do dimensionality. So vacancy 0D, self-interstitial 0D, 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 edge 1, 2D. What else? Void is the 3D. Frankel pair, those are 0D defects. I'm going to cross these out because we don't have an ionic crystal here, so those will not be seen. Where's there a vacancy? There's a vacancy, there's a vacancy. So we can see that there. A self-interstitial, so an atom that's kind of occupying another point that we kind of see here. There may be a couple little self-interstitials in here that are kind of disrupting the crystal. So you can kind of try to see that there. An impurity interstitial, I can see an impurity interstitial is trying to sit in the lattice just right. And actually, we can't really see a clear impurity interstitial because it's not really sitting in between those sites. Maybe in here, but again, you're not seeing the different types, so I don't really see here. Impurity substitutional, oh yeah, here we go. Right here, right here, right here. Those bigger atoms, they look different. We got that one. So let's go ahead and let's take a peek at any substitution, or that would be the, the substitutional impurity atom. Edge dislocation, we can see a little bit of an edge dislocation right here and right here, where you get that extra half plane kind of shoved in. Grain boundary, here's a grain boundary. You can see kind of multiple ones. A little grain boundary right here. You can see a little grain boundary right here where the crystals, again, start to kind of shift in terms of the angle between them. So for example, right here, then shift down. And then voids, don't see any voids here. All right, let's get on to number 2. So for number 2, I have 3 different mystery materials, X, Y, and Z. They're all metals. They have activation energies of these. So activation energy, remember, we had our concentration of vacancies is equal to the exponential of minus QA, which is the activation energy, over KT. K is our Boltzmann's constant. It's equal to 1.38 times 10 to the minus 23 joules per Kelvin. If it's in electron volts, 8.617 times 10 to the minus 5 EV per K. So with that, the question is asking us, for each material, what is the concentration of vacancies, room temperature, and 1200 K? So with that, let's go ahead and let's start to calculate that, and we will use mathematics. So let's put in our equation, and I'm going to say, let's see, I'm going to do our QX. So QX is equal to 0.2. QY is equal, QY is equal to 1.1, and QZ is equal to 2.1. So, and my equation is going to be XV is equal to exponential minus QA divided by K is our Boltzmann's constant. Let's go ahead and define that. K is equal to 8.617 times 10 to the minus 5, because I want to work on EV. And then we'll do temperature as well, over K times capital T. So XV slash dot, and I'm going to just do QA, replace that with QX, and T goes to room temperature, 298. And you can see those for here. The only thing we could change is Y. You can see huge, that exponential, that Arrhenius relationship is ridiculous. That's quite a bit. But it also kind of changes with temperature as well. So 1200 K, so we can go here, 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 and you can see how they're going to increase quite a bit. Oops, I don't want number 4. Here, and then here. All right. How might you expect the concentration of vacancies versus self-interstitials to differ, and how can you account for this in your calculation? Well, the activation energy is going to change, so it's much easier to create a self-vacancy than a self-interstitial. Or a vacancy than a self-interstitial. So we would expect them to be, self-interstitial should be much, much lower because the activation energy will be a lot higher because it takes more work to get that in. All right, now to actually, we can kind of do this quite quickly before we get into our deep Frankel defect discussion here. So, write the Frankel and Schottky defects for TA205. So, for the Schottky, we'll have null goes to vacancy of TA plus vacancy in oxygen. That's always going to leave the 2 plus here. Vacancy here is going to be 5. 1, 2, 3, 4, 5.
There's going to be 2 of these, there's going to be 5 of these, and we're done. So for the Frankel and Schottky, or actually for the Frankel, this is the Schottky right here. For the Frankel, we will have that basically TA X goes to vacancy TA 1, 2, 3, 4, 5 plus TA interstitial 1, 2, 3, 4, 5. And then oxygen X goes to vacancy and oxygen 1, 2 plus oxygen interstitial, and then that's 1, 2. All right. The enthalpy formation is 0.8. The Frankel is this, which will be the dominant reaction. Schottky, lower activation energy, more of those reactions as we just saw previously. Hence the point of that last problem. All right, now to our favorite exercise. So we're going to write out the 3 defect reactions for the incorporation of Al2O3 into CaO. Frankel and Schottky, these defect reactions are the bane of existence, Kroger-Vink notation. All material science students don't like it, but it should be fine. So Al2 into, so my impurity Al2O3 into CaO, Al2O3 into CaO, Al2O3 into CaO. So one must have an anion vacancy. So my anion is basically my oxygen. So vacancy here, 1, 2. So one must have that. Okay, so that's it. That's all we're given. So anion vacancy. So I've got it. So I need to put something that's going to be positive. So I'm going to do plus Al replaces. Actually, I'll do that a little bit later on. Actually, I'll do that right now. AlCa. So Al is 3 plus, Ca is 2 plus. And so Ca is 2 plus, Al3, oops, so that's going to add another positive. That's not good. But we can always just basically say I want to do plus vacancy in Ca. That could leave me with basically a 2, a minus 2. So let's see, I have now 2 CaOs. So that could leave me, I'm just trying to see now how I could actually do, let me put in 2 here, and I could do a 2 here. So this gives me charge balance because I'm 2 positive here. I am 2 positive here, and I'm 4 minus here, so that's okay. I'm just going to zoom out a little bit. So let's do across here. So I have 2 ALs, great, and I need plus 3 oxygen X. So I'm cross clear here. What about here? I have an oxygen, 4 oxygens, 4, done. All right, what is the next one we need? We need to have a cation interstitial. So I'm going to do Al interstitial, and I'm going to do, this should be 1, 2, 3. And then I'm just going to do plus vacancy of Ca, 1, 2. So I need 2 of these, I need 3 of these. That'll give me my charge balance, plus 3 oxygen X. This will be 3, and that's it. And then finally, I need a substitutional cation. So I'll just do what I had previously, 2AlCa, and then let's go ahead and charge balance this guy with what we know how to do, but we'll do something a little bit, actually, we could do something very simple here. So we could just do something like we did previously, but let's get a little bit tricky. How about plus, I'm going to do an oxygen interstitial, and then I'm going to do, this is an anion, they ask for cation interstitial there, 1, 2, and then that is going to, let's see now, actually that should be fine, except for, actually let's go ahead and keep counting. So we actually have everything we need here, but we need another, actually we're okay. So 2 oxygen X, that should be, yep, we are good. So charge neutral, 2 ALs, 3 oxygens, Ca, we need 2 Ca, 2 Os, that's it. We have got it. So we need to do the same thing effectively now, but with, let me erase this here, erase this here, let's erase here. So now we've got to do, I need it for MGO into TA205. MGO into TA205. MGO into TA205. So, anion vacancy, so plus, so let's do actually vacancy oxygen 1 2 actually, oops, excuse me, dot. So I'm going to do similar strategy. I'm going to put Mg on TA. TA is 5 plus, it goes, so that's going to be a minus 1 2 3. So I want to just try to do a charge balance here, so I could do a 3 here. So for example, I could do a 3 here, I could do a 2 here, and there should be good. I have 2 MgO, so I need 2 oxygen X. What are my oxygens there? 5, TA205, we're good. What about cation interstitial? So let's do an Mg interstitial. That's going to be a 2 plus. So, and I could do, basically, I could actually do now, let's do a vacancy in TA. So that's going to be 1 2 3 4 5. So I could do 2 here, I could do a 5 here, plus 5 oxygen X. So 5 TA, 5 MgO, 5 oxygen, TA2, 5, we're good to go. And then finally, the substitutional cation, so Mg, TA, 1 2 3. And then I'm going to do an oxygen, actually, I'm going to do, how about a TA interstitial? But that will, actually, that'll be fine. So I'll do 1 2 3 4 5. I actually don't like that. But let's see if we can work around this one. So instead, why don't I could do the vacancy and oxygen again, but why don't we stick with that? TA interstitial. 1 2 3 4 5. So that's a 5. So how about this? Plus a vacancy in oxygen will give me a couple more. Actually, I'm not going to do the TA either. I am going to do, can't do the TA because we don't want to create the interstitial there because our charge balance will be messed up. So instead, let's take a different route. So let's go ahead and let's add a plus Mg interstitial. So that's going to be a 2 plus. So let's add 2 here, let's add 3 here, and we may be in some good shape right now. We can balance the rest. So we see we have 5 Mgs, because we have 2 here, there you go. Let's go 5 oxygen X, 2 TAs, 5 Os, we got it. All right, and then finally, draw the Berger circuit for the figure here, determine present, selection of the unit tangent vector, start finish, all that good stuff. Okay, so let's zoom back in here. So I don't see anything on this plane where there's a defect, can't really see over here, so I'm going to use this. My tangent vector is going to be pointing out of the board here, so I'm going to pick basically the start of my circuit. So remember, I want to kind of be selective here, so I'm going to go here, and I'm going to go right-hand circuit, so that's my start. 1 2 3 4, 1 2, so 1 2 3 4, 1 2 3 4 5 6, 1 2 3 4 5. So I'm going right hand, 1 2 3 4, actually 1 2 3 4 5 6, 1 2 3 4 5 6, 1 2 3 4 5 6, and I went 4 this way, so I need to go 1 2. So I know that's my finish. I draw start to finish this way. It's a line, it's a screw, it's parallel. My tangent vector is parallel to my Berger's vector. So that's a right-hand screw, RH screw. What about here? I don't see anything going on here. I do see something coming out here, so I'm going to go out of the board. I'm going to pick a point basically right here. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. Tangent, Burgers vector. Perpendicular. What does that mean? Screw. What about here? Well, actually, let's see what we've got here. This is going to be, I'm going to go right here, and I'm actually, let's see, I'm going to go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3. I'm actually kind of stuck here. So because this is a full, basically, this is perfect here, this is perfect here, but we just have the full step. So it's a whole plane. So it's not really a defect because we're done. It's not that extra half plane like inserted in there. So that's the step left behind for a full dislocation. So that's it. So edge, right-hand screw, and that's all we've got. So I will see you all next time on Pset 4 Solutions. Thanks. Bye.